Next up, Deep Dive into Windows Relaying Attacks by Bojan Zdrnja.
Okay, right. Hello, everyone. I see people ran away from Windows, but that's okay, unexpected. Anyway, my name is Bojan Zdrnja, and it's great to be here again at BalCCon. Just short introduction about myself, and then we're going to dive deep into Windows. So I'm the CTO of a company called Infigo, where I lead the penetration testing team. I'm also a SENS certified instructor. I teach the web application pen testing course. Also one of the Storm Center handlers, but this is something that we can talk about later during the party. Let's dive into Windows and how authentication in Windows actually works. So first of all, why this talk? A lot of people in my team as well, and people that I had some discussions with, used to perform some internal penetration tests, red team engagements, whatever. And today, almost always you can see some Windows servers. So no matter where you go, I almost still have to see a company that doesn't have a single Windows server running, right? You can see them here and there. I think you even have them in Apple. So we almost always have Windows servers running somewhere. And whenever you attack Windows environments, there are a couple of tools that almost every single penetration tester will use. One is Responder, the other one is anything from the in-packet repository, things like NTLM, RelayX, and a couple of other well-known tools. And most people just run those tools without actually understanding how the vulnerabilities that they're exploiting work. And I was one of those people as well. You know, you just run a command, doesn't work, okay, let's add a new flag, or you find something on a net, you add another flag. Oh, now it worked, excellent, I hacked that. But the question that I had was, why did this work in the first place? So that's why I decided to dive a little bit deeper into the Windows authentication mechanisms. So specifically today, I'll be talking about NTLM authentication or pass-the-hash attacks, but we'll actually see the network packets. We'll see what kind of crypto algorithms are being used by Microsoft. And hopefully, once I'm done with this talk, everyone in the room here will actually understand how that works. So if you ever encounter a problem in the future, you'll hopefully be a little bit one step closer to resolving it. As I'll go through some quite technical things here, I actually suggest if there is something that you don't understand, you perhaps ask me immediately, or we can do that at the end, whatever works better for everyone. But again, my goal is for everyone to fully understand how NTLM authentication works and why these attacks actually work. So before we start, before we take a look into packets, just a little bit of terminology here to make sure that we are all on the same level, so we all understand which components of the authentication mechanism I'm talking about. So today, when you log into Windows, doesn't matter if it's a domain login or your local account, when you enter your password, hopefully that password will be saved only and exclusively by using a mechanism which is called anti-hash. So what Microsoft will do is that they will take your password, they will convert it into Unicode UTF-16 little endian, and then they will perform MD4 hashing algorithm over your password, and they will store that. On your local Windows machine, it's stored in your SAM database. If you log in via Windows domain, it will be stored on your domain controller in another database called NTDIS. That's everything that Microsoft does with passwords. There is no salting. There are no strong crypto algorithms. They still use MD4, which is one of the reasons why today, if someone gets your hash and your password is relatively weak, it's kind of easy to crack it. Because MD4, that's unbelievably fast. And I think that Milan will have a cool presentation about that tomorrow. So our two presentations kind of go very well together. The old version, LM hash, that is horribly broken. And if you see that, you do a little bit of dancing around because that's like very horrible. new Windows systems don't use that. Now, that's called anti-hash. That is the way how Microsoft stores our passwords. When those passwords are exchanged over the wire on the network, we have several authentication mechanisms on Windows. Modern Windows environments will generally use Kerberos, but due to support for everything that Microsoft does all the time, there will be one older authentication mechanism, which is called NTLM, which then exchanges our password hashes, which are again hash. We'll see how in a couple of minutes. But the hash that you actually catch on the network, just for terminology's sake here, is called either net NTLM version 1 or version 2. So anti-hash is what our password is hashed into. When we catch this on the wire, it's called net NTLM version 1 or 2. That's important just so we understand how things work later. So the NTLM protocol, and I'll have a couple of slides about Kerberos, but NTLM is what we're interested in today, is a challenge response authentication protocol. Microsoft made this obviously popular, and the goal of NTLM was to allow authentication between two entities, your laptop and a server, without directly sending password over the wire. So we have a challenge response protocol here, which actually consists of 3 messages, as we will see. What's important is that at no point in time is our password ever sent over the wire in plain text. That's very important. It's not even sent over the wire as pure MD4 hash, because that would be horrible as well. So they do some kind of calculation to obfuscate or encrypt that. The NTLM protocol itself, as I said, since it's a challenge response protocol, it consists of 3 messages. So when you click on a share in your company, if Kerberos is not used, and I'll talk about cases when Kerberos is not used, so if NTLM is used, what happens is that your laptop sends a challenge message to a server, the server replies back, negotiate message to the server replies back with a challenge message. Now your laptop calculates something, because it knows your password, and sends back so-called authenticate message. The server now verifies if the calculation is correct, and if it is, the server knows that you know the password. We'll see what it looks like on the network in a second. The challenge that we use here to calculate something as proof of knowledge of our password is usually just an 8-byte value, 64-bit random value. Again, we'll see that in a second. So if you remember a couple of slides ago, I mentioned that there are 2 versions of the NTLM protocol, version 1 and version 2. Version 1, when it was introduced back around Windows XP and Windows 2000, and again, it's quite insecure. We'll talk about NTLM version 2, which is what modern versions of the protocol use. But with NTLM version 1, what Microsoft used was the following. They took your anti-hash. Remember, anti-hash is just MD4 of our passwords. Anyone knows how many bytes you get from MD4? Anyone? Come on. Yeah, that's correct. But you are so shy. It's 16 bytes, right? So you get 16 bytes with MD4. Now, Microsoft needed 21 bytes. Why? Because they needed to encrypt 3 parts with 7 bytes, which is a DES key, DES algorithm key. So what someone in Microsoft decided to do is, hey, how about we add zeros, right? Remember from the previous talk from Travis, you just add zeros at the end always. So they just null padded this to 21 bytes, split into 3 parts of 7 bytes, and they used those as encryption keys for challenge with the DES protocol. Very, very old DES protocol. So if you ever see this on the wire, right, because that's authentication protocol, we can actually take whatever is on the wire and try to crack that. And with today's CPU power, GFX power, you can actually crack this almost instantly. Not instantly, but it will take you perhaps a day. Very, very insecure. Especially the last part, because what's the last part? The last 2 bytes of your MD4 hash and 5 zeros. We know it's always in the last byte. So NTLM version 1, if you see that, game over. Get rid of that. It should die. Now, NTLM version 2 That's a little bit better. It's actually way more complex. So what Microsoft did with NTLM version 2 is that they take username and target name, they convert it to Unicode, they concatenate it, and then they use couple of rounds of HMAC MD5. So HMAC MD5 is a hashing algorithm which has a key as well. That key, you can probably guess, will be our password or the anti-hash of our password, right? They have a couple of juggling with crypto over there, and that's what they use for authentication. We'll talk about that in a second, and we'll see what it looks like actually on the wire when you have your Windows laptop and you connect to something else. Now, just remember this last bullet here. In NTLM version 2, there is message integrity control. So those 3 packets, these 3 over there, right? Those 3 packets will also have their integrity protected. That's important for those relaying attacks. All right. One last thing before we dive into packets is pass-through authentication. And what is pass-through authentication? Again, remember when you log in to a Windows domain, perhaps in your organization, authentication is handled by your domain controller. And you click on a share, which is on a member server, a server called share, for example, because that's where you have all of your files, all of your data. Now, when you click on that server, well, ideally it should be Kerberos, but let's say it's not, so it's NTLM. When your laptop, your client, sends a message to that member server and says, hey, I want to authenticate, and my name is user Bojan, whatever, that server has no idea what's your password. It has to ask someone. Who? The domain controller, right? So it will ask the domain controller, hey, is this password correct or not? And then the domain controller will say yeah or no. This is called pass-through authentication. It's been there forever. And one of the things that made me create this talk was, how the hell does this work, right? I wanted to see how this actually works and what Microsoft does this. So what I do in the backend, and again, we'll check about crypto stuff here as well, they use actually RPC. So that member server that needs to verify your password will use a remote procedure call to a domain controller. It will actually just pass all the NTLM packets over there, and it will tell domain controller, hey, verify if this is correct or not. And it gets back yes or no. We'll see how it works in a second. This is what it works on the wire, right? Our client first talks to the server. We have NTLM, negotiate, challenge, authenticate. Then the server asks the domain controller, is this okay or no? And if it's okay, then you can access your file on the share. Notice here that we actually have a couple of protocols that are being used. And with NTLM, as we already actually mentioned earlier, the thing that we need is just the MD4 hash of the password called the anti-hash, which means that in order to authenticate, I don't need to know your password. If I get the anti-hash of your password, MD4 hash, by any way, and you can have a password which is 78 characters long, and you spend half an hour every morning logging in, right? I don't care about it. All I need is your password hash. I don't care how strong your password is. And this is one of the dangerous things about relaying these attacks, and we'll see in a few minutes. There's another observation here. If I'm sitting somewhere on your network, and I somehow get your client to talk to me instead of the target server, I can actually relay that connection to a different server. Because by default, hey, it's Microsoft, these two sites will not check with whom they're talking with. So the client will not verify if it's talking to the server that it wanted to talk to, and the server will not care about who it's talking to. By default, with Windows 2022, so with the latest one, right? And this is why we will be able to very carefully exploit this by kind of sending those connection attempts to different servers. Ooh, so imagine this. You clicked on a share that perhaps doesn't exist. I somehow caught that request, and I relayed your request to another share. Your client will successfully authenticate because you have the correct password. The connection will go through me, but now I can access that second share as you. And that's why this is so dangerous. I see this all the time. In almost every organization I visit, I've never seen in my life so far that NTLM was completely disabled, which you can do. It's just a GPO setting. You just set it up. I've never seen an organization that completely disabled Kerberos. If anyone can see that, let me know. And it's like amazing. Every single time this kind of works. So let's see how it works. All right, so this actually applies to any protocol that can use NTLM for authentication. And Microsoft was so great that they allowed NTLM to be used as authentication on different protocols. So when you click on a share, it will be Samba, SMB. When you go to your SharePoint portal in your organization, it might be NTLM over HTTP. When you go to LDAP on a domain controller, it might be NTLM over LDAP. All of this can use Kerberos as well, but NTLM will generally work. So we need to make a distinction between the carrier protocol, which is SMB when you click on a share, and the authentication protocol, which will be NTLM over here. So these protocols will actually have two components, like, right? Authentication, which is NTLM, and session, which is where we actually do something. So let's see what happens when we click on a share on a Windows machine. This first packet is being sent by your client, and this here, I can actually use this. This was sent by Windows 11 with all patches installed just a week ago. And there is one very important flag over there in an SMB packet which says security mode. And it has two settings, signing enabled and signing required. Signing is the mechanism, again, as we'll see later, that allows us to verify who are we talking to. And ideally, the second one, signing required, should be set to what? True, right? But guess what? The very latest Windows 11 doesn't set it to true. The very latest Windows Server 2022 doesn't set it to true. They set it to false, not required, but supported, enabled. Why does Microsoft do this? Because they will probably break half of the world if they just enable that. So they leave this to end customers to do. No one does it, right? That's how it works. All right, so this is what the client sends. This is what the server replies back. This is Windows Server, in this case, Windows Server 2016 with the latest patches. Again, enabled true, required no. So at this point in time, we established an SMB session. Now comes authentication. So this is my client. It sends negotiate message. There's nothing here that's interesting. Actually, there is one thing. There's another field here. See these negotiate flags? This contains another flag which says that NTLM signing is enabled. This is important for something later, so just perhaps remember that. All right? Now, oops, sorry. The server replies back, so this was the client request, nothing important here. The server replies back with our challenge, which should be somewhere here. And now, oh, I'm on the wrong, there we go, sorry, wrong slide. So this is the response from the server. See the server challenge. So these are the bytes that will be used for some encryption. Random bytes, doesn't matter what they are. The server sends this back to us. Now, this is what our Windows client actually does. If we have NTLM version 1, then we have some simple calculations, but ignore that. If you see NTLM version 1, that's horrible. If we are using NTLM version 2, which is what every recent Windows machine should use, then we have quite a bit of calculation here. We have the server challenge, which are those 8 bytes that we saw in the previous slide. Then the client will come up with some random 8 bytes. We'll take our domain name. We will take our timestamp. And then we'll have 2 HMAC MD5 calculations over here to get the so-called LM version 2 and NT version 2 net NTLM hash. The first one, LM version 2, is usually ignored. this is the one, the second one is the one that matters. Notice that at no point in time in this calculation, we have the server name, right? We have the username, we have the domain name. There is no server name that we want to connect to. So the calculation itself does not take the server name into any calculation whatsoever. Now the client calculates this, your laptop, and sends the final authentication packet over here. And notice that we have here the response, we have the client challenge that we created, couple of other values, and so on. And there are some extended attributes that we can send over here, and this is the fun part about Microsoft as always. Notice the one at the very bottom called target name. In the authentication protocol, NTLM can be extended with these attributes where you can actually specify, hey, I want to authenticate to a machine with the IP address of 192.168.100.130 over CIFS, which is SMB. But if signing is not enabled on the carrier protocol, actually not required, sorry. Remember the carrier protocol SMB. The server will say, I don't care about this. That's not my name, but I'm going to authenticate you anyway because I got that packet, so I'm going to do it. I'm a nice guy, right? That's how Microsoft does things. Right, so at this point in time, the server has no idea whether our password is correct or not. And now we use the secure channel. The member server will talk to the domain controller to verify our password. And this is one thing that I wanted to actually see or understand how this works. So let's dive into this, prepare for a little bit more weird crypto because it's Microsoft after all, right? So as I said, we use RPC, remote procedure call, between that member server and the domain controller. They need to somehow encrypt data. And this is kind of funny. In order to encrypt data, every single server in your Windows environment will use a session key that it will calculate randomly, and it will change every 30 days. 30. So that session key will be valid for 30 days. When you boot up your Windows server, it will talk to the domain controller instantly, authenticate to it for secure channel, generate the session key, and now it will use that session key for 30 days. After 30 days, or if you reboot the server, a new session key is generated. Okay, that's how it works. So let's see how they generate the session key. The server sends one packet to the domain controller, this one over here. It contains client challenge, 8 bytes of something. The server sends back its own challenge, additional 8 bytes of something. Now, both sides take the client and server challenge, concatenate together, and you get nice 16 bytes. That's the thing at the bottom. This is called data vector. So what they do in the next phase, they do the following. Each of them takes the server's computer password. So you know that every single computer that you have in a Windows domain, it doesn't matter if it's a workstation or a server, they have their own computer password, right? You've seen that. Server name with $sign at the end, right? That's your computer account. Every single computer account has its own password, which is MD4 hash, right? As anything else in Windows. It's just random and long. We can't crack that. That's fine. Now, your member server knows its own password, of course, and the domain controller knows that member's password, well, the MD4 anti-hash of it. So they do the following. They take the data vector over here. I just took the value. I'm using XXD to convert this from hex into raw bytes, right? And then I'm using OpenSSL with HMAC SHA-256 algorithm this time, with key, which is the server's password. Make sense? Everyone following so far? Okay, because it's important for the next phase. Not too difficult, right? Then you get out a huge blob, because it's HMAC SHA-256, and Microsoft decided, oh, let's just take first 16 bytes, because 16 is a nice number. So they took 16, they just take first 16 bytes from this over here, from the calculated hash, and this will be called session key. And this is valid for 30 days. So after 30 days, what usually happens is that your computer password gets changed and a new session key is calculated. Now, I've seen some domains, since you can configure this, where administrators said something like, ooh, I don't want that session key to be changed. I don't know why, but they want. So they extended the time. So I've seen sessions where the validity of session was like 1,000 days, because they can change it to any value. Now, we calculate something over this, and we have the session key. The server does the same thing, because the server knows the domain controller knows our member server's session key. And in order to prove to each other that they know each passwords, they take that challenge that was sent at the beginning, the first packet. Where was it? Over here. They take the challenge, they encrypt the challenge with the session key, and send to the domain controller. So this is it, right? Notice that what I'm doing here is I'm taking the challenge at the top. Again, just convert this into raw bytes, and then I'm using OpenSSL with a weird algorithm, and this kind of caused a couple of sleepless nights for me. It's AES 128, but the mode they are using is cipher feedback, CFB, with 8 bits. Actually, for this presentation, I wanted to give you CyberChef recipes for every single encryption, but this is not supported by CyberChef, right? So, had to use OpenSSL. It supports cipher feedback mode, but only with 128 bits, which is the default one. Microsoft decided to use the 8-bit one. So what I'm doing here is I'm encrypting the challenge with the key, which is the session key, and my IV, which is just zeros, right? I send it to domain controller. Domain controller does the same, sends encrypted data back to me. I can decrypt it because I know the session key. The domain controller can decrypt it because it knows the session key. And now both sides know the same session key, and they actually prove to each other that they know the password. This is kind of cool, right? Not bad. And this session key is used for every single secure channel authentication for the next 30 days. So if I go back here, see this netlogon network info, where my member server talks to the domain controller. What the member server does now is that it takes those 3 NTLM packets, puts them into one big blob, encrypts it with this session key, and sends it to the domain controller and says, hey, buddy, can you please check if this password is correct or not? It's not that simple. Now, Microsoft does some other Microsoft things over here, as you will see in the next couple of minutes. So this is that packet. This is the remote procedure call. You can see over here the function, which is netar logon semlogon x, and there is just a binary blob. And this is what kind of made me do this presentation. I wanted to see what's in that binary blob because I'm curious by nature. I want to see what's there. I want to know how it works. So after like, I don't know, 4 weeks of reading Microsoft documentation, which is horrible, and checking some other things on the network, there's surprisingly little information about this, even though it's all public. So Microsoft actually, posted documents which explain how this works, but good luck reading 170 pages of, RPC documentation from Microsoft. So I wanted to see how we decrypt this. And now this is what's kind of fun, and I'll just have enough time to go through that. We actually can go through a few minutes over because I think there's plenty of time to the next talk. So we need a couple of ingredients here. So check what I do. The first bullet over here, and I can actually use my laser pointer. Yep. So the first bullet over there, this is our session key. Remember, the one which is valid for 30 days. So both sides know that. Then, on the previous slide, over here, you can see 2 values, something called sequence number and packet digest. Now, those names make no sense whatsoever, and Microsoft agreed with that. So what Microsoft did was that they took the value called packet digest, they concatenated twice, and they said, oh, this looks like a perfect initialization vector. Okay, why do you call it packet digest then? I would call it just IV. Then they have another value called sequence number, and this is actually the proper initialization vector, which is encrypted. Come on. And they use the same algorithm as before. So what I wanted to do is the following. I took this value, which from the previous file, previous slide, is the initialization vector encrypted. Again, just convert this into row bytes. I'm using the same algorithm over there. You can see -d, which is decryption. -key is my session key, the one that is valid for 30 days. And my IV I got from the packet, which was again that packet value number concatenated twice. And now you decrypt this value, and you actually get the real IV that you can see on the screen over there. So when I managed to do this, and I actually saw some real numbers, I was like, finally something. Because with this crypt algorithm, when you decrypt something, you always get some garbage out, right? There's no padding here in the crypto algorithm which will tell you, hey, your key was wrong. No, whatever key you put, you get some garbage out. But when I saw zeros and 8, I was like, okay, this looks like something that a human being would do. Then Microsoft does the following, because why not? They take the session key, and this is like the most pointless thing for me ever. They take the session key and they XOR it with F0. Like, adds absolutely no value to any security over here. And every single server in the world does this all the time. All the time. So they just burn a little bit of cycles for nothing. So you just XOR with F0. You now get new session key, which again is being used like this. And we can take that binary blob that was quite huge, decrypt it again. This time, this is the key, session key XORed with F0, no reason whatsoever. The IV is what I got over there, and I just redirected this to a binary file because it's binary contents that I got back. So finally, I figured out what I got there. It's binary, so I couldn't show everything on the slide. So I just did strings on this with UTF encoding little endian. That's what Microsoft likes to use. And notice that in that exchange, at the end, there's actually the proper IP address that I wanted to connect to. But when I relay someone to a different server, it still works. So I was like, why does this work at the end? Because they don't care. If you don't put signing on required, everyone in the whole story will see that there is incorrect target server over there, but they'll say, well, fine by me, right? Who cares? Signing is not required. I don't care that this is not the correct server. So everyone will ignore this. So why is this important? Let me actually go to this slide first. This is what the attacker will normally want to do. And this is why the whole story is so dangerous. So when you come to your office, it will be always, for an attacker, most interesting to attack you in your office because that's where other juicy servers are. And you click on a link or a share or a name that does not exist. What your Windows machine will do by default is that it will first try to find that name in DNS. It will fail. And then, since Windows are very helpful to a user, your workstation will send a broadcast and it will say, hey, is anyone attacker? And the attacker will say, yep, over here, come to me. So your client will send the initial SMB packet, remember the top layer, to the attacker. And now all the attacker needs to do is just send that packet to a different server, as we can see over here on the slide. Right? So I'm just relaying this to dash share. The share server, if signing is not enabled, will send a challenge back. All I do is just relay the challenge back to the client. The client calculates all of this, sends back to me, I relay that to the server, and if signing is not enabled, the server will say, oh, thank you very much, your password is correct, here is access to your files. And now, since the session is going over me, I can read all of your files. We'll see in a few minutes how dangerous this is, and I should be able to finish on time. So again, the biggest problem here is that even though the NTLM protocol, if I go all the way back over here, see the bottom bullet over here. Even though the NTLM protocol contains message integrity code, which means that an attacker cannot modify NTLM packets. They are protected with integrity. You can't modify anything because the whole HMAC MD5 thing will fall apart. And even though NTLM by default will always have signing enabled, remember on the NTLM level, on the outer level, over here, SMB will say, well, I don't care about signing. So in order for signing to work, both of these layers have to have signing enabled and required. If it's not, then they don't care about signing. And this is what allows us, if I then again go back here, this is what allows us to juggle with these packets. I can't change NTLM, but I can change SMB. So notice over there at the top that I can even change things from signing enabled to signing enabled false. So the server will think, oh, this must be some very old client because it doesn't even support signing in the first place. I can change SMB because there is no integrity protection on the SMB level. I can't change NTLM, but I don't care because if I change SMB to not signing supported, then the other server will just authenticate us. Was this clear to everyone? All good? A little bit of crypto. It's still early in the day, so good that they moved me earlier. Not as much drink yet, right? So let's see how we can exploit this. And again, if anyone here does any network pen testing, these will be the tools that you are very, very familiar with, but I wanted to check why they work and how they work. So again, with these authentication attacks, if signing is not enabled, then we can kind of relay things around. And what I normally do when I come at a client is to enumerate the target list of servers. I set up a listener, and for any authentication that comes to me, I just relay it to one of those servers from the list to see if there is some juicy information over there. You can relay to almost any server as long as it doesn't support signing. That's the only important thing. I could, in theory, perhaps even relay to your Exchange servers, maybe through Outlook Web Access if some things are not correctly configured. What do I get? I get access to your emails. Remember, I don't do anything with authentication. Your workstation will happily authenticate to the target server. So the question is, how do I get you to come to the attacker's website so I can juggle with packets, so I can relay them somewhere else? Well, unfortunately for us normal people, and luckily for attackers, Windows go out of way to make it as easy as possible. So these two protocols, link local multicast name resolution and NetBIOS name service, are, guess what, enabled by default, which means, if I go back to the story from 10 minutes ago, if you click on anything that doesn't exist in DNS, Windows will revert back to these two protocols, and Windows will send broadcast asking, hey, who is machine ABC? And the attacker says, hey, it's me, right? So that's how the attacker gets you to talk to their own machine. How do we get your machine to send a query for something that doesn't exist? I don't know, I could send you an email perhaps with a link to something that doesn't exist. If you click on that, your Windows machine might open Explorer and try to connect over there. So that's how I get people to go there. There are a couple of other things. So the last one is very dangerous. These are the tools that you want to play with. Responder, in-packet, CrapMac exec, and MIDM 6. I think Milan will mention Responder quite a bit tomorrow, so that will be cool. Knowing him, probably live demo as well. Yeah? Cool. So there will be a live demo as well. I was too scared about live demos, so just screenshots over here. So this is what Responder does. Responder basically just sets up a listener, and then for any single name query that comes to Responder, Responder says, hey, it's me, come to me, right? So that's how you get people to come to your own machine. And with Responder, you can either catch those net NTLM hashes and try to crack them, or I can use Responder as a means to get workstations to come to me, and then use another tool, which is from the in-packet library, called NTLM RelayX, to relay them somewhere else. So in-packet, amazing, amazing library. So the people behind this, really amazing stuff that they did, like full implementation of Microsoft protocols. There are a bunch of tools, so if you will be into these network pen tests, definitely a tool that you want to be very, very familiar with. And it allows us to set up this attack just by entering one single command line. Here it is. Let me zoom this a little bit. So all I'm doing here is telling NTLM RelayX to take any incoming connection and relay that connection to this target server, which is 192.168.100.220, and please also support SOCKS. Why do I want to support SOCKS? Because once that authentication happens, by having SOCKS support, I will be able to use my own Samba client to connect to the share, browse the share, as if I'm that user, right? And it does all of this for you automatically. As I said, the only requirement is that signing is not enabled. So we can use a couple of tools to figure out where signing works and where it doesn't. Like you can use crackmap.exec, or you can use nmap with a really nice SMB2 security mode script. If I zoom this again a little bit, this at the end, the server called logos. This is Windows 2022 with all the latest patches from last week. And if I move to the right, signing, hey, false. Thank you, Microsoft, so much, right? So it doesn't work over there. Just a few more minutes and I'm done. Now, as I said at the beginning, NTLM is an authentication protocol. So how about we take NTLM from SMB and we move that, we relay that to a different protocol. Can we do that? Why not? NTLM is always the same. It's challenge response. Those three packets are always the same. So I could, in theory, get someone to connect to me via SMB and then relay that to LDAP. The attacker will just establish a connection to LDAP and then juggle with NTLM packets, right? Now, if you try to do that with SMB to LDAP, it will actually not work because LDAP will have signing enabled and required if the client supports signing. And if you remember in the NTLM authentication packet, there were a couple of extra flags, and one of those flags was signing. So you can't relay SMB to LDAP, unfortunately for attackers. But you can relay HTTP to LDAP. Because on HTTP, if you have NTLM over HTTP, and that's how you connect to your perhaps SharePoint server internally, then you can juggle with these packets. And this is again basis of many, many, many attacks today. You probably heard about Petit Potam, which was a big thing a year or two ago. The whole idea behind this attack was to make a domain controller actually send that initial connection to the attacker so the attacker can move it somewhere else. And since it's NTLM, we get session which has been authenticated as NTLM. One last thing I want to mention here, and I promise I have only one slide left, but I think we're fine with time. The last application over there, Mitem 6. Is anyone here using IP version 6? Like 2. Okay, probably the most ever at a conference. Like unlimited number, more than 0. Still very, very rare. So did you know that, you probably did, that every single Windows installation supports IP version 6 by default, right? So it comes installed with IP version 6. Did you also know that IP version 6 has priority over IP version 4 on Windows? So if you don't support or don't use IP version 6 in your organizations, when you boot up your laptop, and if I can, for example, have a rogue DHCP server running on version 6, I can give you an IP version 6 address, I can give you a DNS server over IP version 6, which will be me. And no matter what your organization set up for IP version 4, your Windows workstation will use IP version 6. It has high priority. By default, every single Windows. You can disable IP version 6. And some time ago, I was actually recommending people do that until Microsoft had an article which says, we do not recommend that you disable IP version 6. So you can do it on your own risk, right? What I suggest that you do, if you don't use IP version 6, is that you change configuration so IP version 4 has higher priority. You can do that on Windows, but it needs to be done, right? It's not there out of box. Very, very nice way for an attacker to hack your machines. Because remember, if I am your DNS server, I decide where you go to. I can tell your machine, every single server is me, and then I relay you to the target server I want to attack. How about Kerberos? This doesn't work with Kerberos, because with Kerberos, we will use service tickets to authenticate, and service tickets will be encrypted by domain controller with the target service, so I can't relay you to another server. I still can on the network level, but it will not work, because the encryption will not work together. There are some very clever attacks that are using some ways to kind of get certain relaying with Kerberos, but I would probably need another 45 minutes for that, so if that's topic for next year's BalCCon, let me know later. And just a couple of conclusions. When you go back home, make sure that SMB signing is enabled everywhere. SMB signing required, shouldn't be too big of an issue. LDAP, channel binding, good luck. Again, I think I've seen only 1 or 2 companies that had LDAP signing fully enabled and required. Even the best companies that I worked with, you enable it and it breaks. Shitload of other things, especially if you have Linux servers, Unix servers, something else that authenticate to Windows, breaks a lot of things. LLMNR, so local link, multicast name resolution protocol, disable it. You don't need it on modern Windows networks. Everything should be in DNS, so disable that. And make sure that IPv6, if you don't use it, has lower priority than IP version 4. If you want a little bit more material, some of these researchers did really amazing research. The Hack and Do one has a lot of things on how this works on the low-level basis. That was one of my inspirations for this talk. And since it's already 17 minutes after 3, I'll kindly shut down my Windows machine so it doesn't send any broadcast messages anymore. So thanks everyone. I hope that you managed to understand this. If not, we can always grab a drink and then forget everything because it's Windows. If we have time for questions, I don't know. We have. So if there are any questions, just shoot. Or Microsoft Crypto, weird things killed everyone and you want to get a drink, that's good as well. Okay. Everyone is scared about Microsoft. Cool, anyway. Thanks everyone. Let's get a break and thank you.